In this tutorial, I am going to show you how you can assemble Chloroplast Genome. This video was made using this online Galaxy tutorial. So I will leave the link to this page in the description box. So basically, we are going to reproduce what has been given here. Most of the activities here, by the way. So just join. And let me also say that the ebook as well as the script for this tutorial are all available on my Patreon channel. So check the description box for the link and then you can use that to get the materials. So take note of that. So before you proceed, I also encourage you to read the introduction here so that you have an idea of what the genome assembly process is. And then you can proceed. So try and then read the introduction here and then we can continue. So once you are done with the introduction, the reading, you need to also make sure you have set up your PC. So you need to have a Unix-like operating system, i.e. Linux or macOS, and you also need to have Anaconda installed. We are going to use Anaconda to install the software packages that we will use. So make sure you have Anaconda installed. I have tutorials that show how to install and set up Anaconda. There are links to those videos are in the description box. So just check them and then use that to set your PC, to set up your PC. So let's continue. So let's move to the terminal and start the exercise. So on the terminal, we will first install the tools. We are going to use Anaconda to do this. So again, instructions for installing Anaconda can be found in the description box. So if you have Anaconda installed, the first thing you have to do is to add channels. So I'll add 2 channels. So I'll say conda config add channels, and I'll add the first one, which is bioconda. I'll add a second channel. So I'll say conda config add channels, and that is conda forge. That is done. I'm now going to create an environment and install the tools I'll use in that environment. So I'll say conda create -n, and I'll say assembly. So this command will create the environment. After that, I will specify the tools I want to install. So I'll say nanoplot. We'll use this for QC, quality control. And then I will say Flye. We'll use this for the assembly. And I'll add bandage. Bandage will be used for visualizing the assembly. And then I'll install BWA, SAM tools, and Pilon. These tools will be used for polishing the assembly. So let's execute this command to install the tools. We are now going to type Y to confirm. Please take note that when you issue the conda create command, it will take some time before this pops up. So just be patient. So it can take about 3 to 5 minutes. So just be patient and then you have this screen appearing. So let's type Y to confirm and then install the tools. Okay, so we will see that some packages are being downloaded. So these are the tools. So Conda will download all the necessary packages, install and configure them for us. So let's wait for Conda to complete its work. Okay, the tools have been installed. So let's continue. Let's clear the screen first. Now let's activate the environment. So I will say Conda activate assembly. Perfect, that has been done. So now we can do a test. Let's just test. Let's just call, let's say, BWA. So I'll say BWA. Okay, so we have been able to run BWA successfully. So the assumption is that all the other tools have also been installed correctly. So we can proceed. Now let's clear the screen and continue. We are now going to create a working directory and cd into it. So I'll say make the Chloroplast. Then I'll cd into it. I am now going to download the example data. So let's go back to the gallery page and look at the download links. So when you are on the page, just scroll down a bit and you find the files there. These are the links. So we have two files. One is Illumina, and then the other is nanopore. Okay, so basically we are going to assemble the long reads. That is the nanopore data. We are going to polish the assembly using short reads, i.e. the Illumina reads, which is here. So I'll download the Illumina first. I'll just highlight the link and then I'll just right click and then copy. You can also download using your browser by right clicking and then opening the link. Okay. I repeat, you can also download the data by right clicking and then opening the link. Okay, so you can do it here, but I will download on a terminal, so that's why I am copying the link. So I'll move to the terminal and then download the first file. So on the terminal, I'll issue the wget command and then I will paste or supply the link, the download link. So I'll execute this command now to download the file. Okay, the first file has been downloaded. Let's download the second file. That is the nanopore data. So I'll go back to the gallery page and then copy the second link, which is this one here. So I'll copy it and then I'll move to the terminal. So I am here. So once I'm here, I'll call the wget again and then I'll supply it with the link. And then I'll execute the command to download this file. So let's wait for the file to get downloaded. Okay, the second file has also been downloaded. So let's take a look at them. I'll do an ls to look at the files here. Okay, now I'm going to do something else. I'm going to rename these files. The names are very long, so I'll try to shorten them. So I'll rename the Illumina. I'll also rename the nanopore. So the Illumina, I'll just call it illumina.fascio. The nanopore, I'll just call it nanopore.fascio. So I'll start with the Illumina. So I'll say mv, and then I'll specify the full name. Then I'll say illumina.fascio. I'll do the same for the nanopore. So I'll use the mv command, specify the file name, and then I'll say nanopore.fascio. Perfect. So now I'll do an ls just to check the file. So they have been renamed. So that's good. We can now proceed. I am now going to move the files to another directory, these files. So I'll create that directory. So I'll say make the fascio. And then I'll move the files there. So I'll say mv star.fascio. And then I'll say fascio. So the files have been moved. I'll do an ls. I'll find a directory called fascio. So in this directory, I'll see my files. Perfect. I'm now going to perform a quality control on the nanopore data. I'll use nanoplots. So I'll say nanoplots, and then I'll say that's fascio. And then I'll supply it with the nanopore data. So I'll say fascio /nanopore.fascio, and then I'll say -o, and I'll say QC port. So the -o here tells nanoplot that we want the reports to be saved in this directory. So this directory will be created. So let's run this command. It will take some time for the QC to be done. So let's be patient. Okay. QC has been done. So let's do an ls, and we are going to find our reports here. So let's take a look at the reports. So in the reports directory, we will have some files, but I would like us to open the HTML file using our browser. So I'll open this one here. So let's do that now. So I'll go to my file manager here and then I'll check the report. So this is the report. I'll open it. Then before I even do that, there's also some information here in the nanostat.txt. Maybe we can start with that first. So you will have some statistics here, and then you can read about them. You can read them. But let's take a look at the HTML file. That is what we really want to do. So I'll open that now and then we can proceed. So this is the HTML reports. So this is the HTML report. It has the information that we opened, okay, recently. So you have some statistics here that you can use to assess the quality of your data, to help you to understand your data. In addition to what has been given here, the guidance tutorial also makes mention of 3 summary statistics that can also be very useful. So the statistics have been listed here. When we check the QC section, okay, the read quality section, and you come here, you have that here. We have sequencing depth, sequencing quality, and we also have read length. So these are things that you can also check to help you to better understand your data and then get an idea of the quality. So you have to check that. There are other tools that you can also use for quality control. Okay, some of them are used for assessing the quality. Some are also used for removal of low quality reads or reads that have read that are short and etc. So you can check the list here and then also check online. There are tools that you can use for quality control. And I've covered some tutorials on quality control as well. So I'll leave the links to those videos in the description box. So that's what we have. Okay. So that is it for the quality control. So I will now move to the assembly parts. So this is the assembly parts. We have that here. We are going to use Flye to assemble the data. So Flye is used to assemble long reads. So we are going to call Flye, and we're also going to give the information here. So we have our FASTQ, and we're also going to give the estimated genome size, and then we will also do something here. This is something that we will do later on. It's not part of the assembly itself, but we will do that after the assembly has been done. So let's continue. I will move to the terminal and then perform the assembly. Okay, so I'm on the terminal now, so I'll first get a new screen. I'll do an ls again, do an ls into FASTQ, and I'll have my files here. So I'm now going to perform the genome assembly using Flye. Okay, so to assemble the nanopore data, I'll say Flye, and I'll say --nano-raw, and then I'll supply it with the data. So that will be FASTQ/nanopore.FASTQ, and then I'll say -o, that's the output. So I'll say nanopore_assembly, and then I'll say -gen to give the genome size. So with the genome size on the Galaxy page, we have this value. Let's take a look at it. So we have 160,000. So 160,000 is going to be 0.16 m. So I'll say 0.16 m. And then we can also indicate the number of threads. I'll say that's C. So the number of threads, I'm going to use 8. I can also use a higher number. If you have a high-end PC or if you're working on a computer cluster, chances are you have lots of cores. So you can increase this number to 10 to 20 or 30 or whatever you want. Okay, so if you have more threads, then the assembly process will be faster. Okay, but if you're using a normal laptop, then you can use 8. Okay, if you use 8 and it's too slow, then you have to probably use a high-end PC or a computer cluster. So that's what it is. Please take note that it is possible to include a polishing step when using Flye. If you want to know how to include a polishing step, you can check the Flye documentation page, or you can check my previous video on Flye. The link to that video is in the description box. Now let's get back to our exercise. So let's run this command. Okay. Now the assembly process has started. So let's wait for everything to get completed. Okay, the assembly has been done. Okay, so you have some summary here that you can read. Okay, just as a starter. Okay, just for the start, so that at least you have an idea of what has been done. So we have total length, fragments M50, largest fragments, scaffolds, main coverage. So this is something that you can take note of. Okay, so now let's take a look at the output. So the final assembly can be found here. So we will just take a look at that. It's still in our working directory anyway. So if I do an ls, I'm going to find this directory which has the assembly. So I can do an ls into it. That's nanoplot assembly. Then I'm going to see some files here. So I have the assembly.first.a which we are going to use. And we also have assembly graphs that you can use. Okay, so if you want to visualize the assembly, you can use the graph. We will take a look at that also here. There's also a log file here. There's also assembly info. These are things you can also look at if you are doing quality control. But let's proceed. We will move on to the next activity. So let's go back to the Galaxy page and then look at what has to be done. Okay, so after assembly, we are supposed to rename the file, the assembly file, but we are going to leave it as it is. This one, we are not going to do anything, but we will move straight to this one here, the visualization. Okay, we will do the visualization first, and then after visualization, we will do the polishing, which is here. Okay, so that's what we are going to do next. So let's go back. Okay, so let's go back to the Galaxy page and look at what we are supposed to do next. So on the Galaxy page, after assembly, we are supposed to rename the consensus output file, but we will skip this. We are not going to do anything here. We will move on straight to the visualization. So we are going to visualize the output using bandage. Okay, so we will use that just to confirm some stuff here. So we are expecting to get something like this, and then with the explanation that has been given here, we will be able to better understand our data. So that's what we're going to do. So let's go back to the terminal. Okay, so what we are going to do next is to visualize the assembly that we have obtained. So that means we will call bandage. We are going to use bandage to do this, and then we are going to supply bandage with this file. This is the assembly graph. So that's what we are going to do. So bandage comes with a graphical user interface, and so I will advise that you run it locally on your PC. So if you're using a remote Linux cluster, I'll suggest you download the assembly files, and then you also install bandage locally and then run it. I have a tutorial that shows how to install bandage, so you can just check the description box and use that to set up your PC. Okay, so I'll go to my file manager and then explore the files a bit. So these are the files, and then the assembly graph can be found here in the nanoplot assembly directory. So I'll open it and then I'm going to locate it. So this is the file. This is what we are going to use. Okay, so now I'll open the terminal again and then run bandage. So I'll open bandage now. Okay, so to open bandage, I'll just call bandage like this, and then bandage will be open for me. So this is the interface. So from here, if you want to visualize an assembly, then we have to come to File, and then we click on Load Graph. Then we will locate our assembly graph, which can be found here in the nanoplot assembly directory. So I'll open it, and then I'll go and then select the assembly graph, which is this one here. So it's called assembly_graph.gfa. So I'll open it. And then after I have done that, I'll click on Draw Graph. And then it will be open for me. So that's what we have. Now let's add some labels. So we will come to Node Labels. We will check length, we will check name, we will check the depth. Okay, I want this to be the same as what is on the gallery page. Okay, with respect to the labels, that's what I have here. So this ones you can customize it. Maybe if you don't want H2, H3, H1, you can give it a different name, or you can give them different name. But anyway, let's proceed. So that's what I have. Please take note that the color that you see here may be different from what will appear on your interface. So take note of that. And also, the image here, what I got is a bit different from what is on the Gallery tutorial page. So that could be due to a number of factors. Maybe the version of bandage I'm using is different, or maybe the content of the assembly is also slightly different. So all these things can lead to us not having the exact same image, but we will have similar outputs. Okay, the images may not be the same exactly, but it will be similar. Okay, so it's possible if you do some tweaking, we can get the exact same image, but that's beyond the scope of this tutorial. So let's proceed. So the most important thing here is that we're able to reproduce what is there. Okay, so there's the image. So from the Gallery tutorial page, according to the Gallery tutorial page, this image here represents a typical chloroplast assembly. And so from the Gallery tutorial documents, my interpretation is that a typical chloroplast assembly will have a long single copy region, which is this one here, and then a short single copy region, which is here. And then connecting these two regions will be an inverted repeat. Okay, and that is what we also see here. So this tells us that we are dealing with a chloroplast assembly, and things are looking good. So far, so good. That's what we have here. Now, if you have this, you can also export the image. So you can go to File, and you can go to Save Image, Current View, or Entire Scene, or whatever. So I mean, that one depends on what you are doing. So for now, I'll just go to this one here. I'll just click on Save Image, Entire Scene, and then I'll save it here. So it's going to be saved in the assembly directory. So I'll save it. So I have it saved. So I will check it out now. So it's here. So I'll open it. This is it. So you can open it. And if let's say you are going to send a report, you can just input this image in your report. So you can have your Word document or spreadsheet or whatever, and then you just add this image to it. Okay. The labels too, you can decide to enable or disable them. That is up to you. So that's what we have. So this is how we visualize a genome assembly using bandage. Okay, so let's go back. Let's continue. So the explanation is here, by the way. Okay, so you can just read about it. There's the Gallery tutorial page. So after you are done with this, you can decide to do this exercise, but I'm going to skip this one, and then I'll move to the polishing section. So what we are going to do next is to polish the assembly that we have generated. So with the polishing, we are going to use three tools. We will use BWA, SAM tools, and Pilon. We will first map the luminal rays to the assembly. And after that, a bound file will be generated. This bound file will be sorted and indexed, and then Pylon will be used to do the polishing. So let's go to a terminal and I'll show you how that is done. So I'll first clear the screen and then I'll do an ls again. So let's ls into the FASTQ directory and see our files. So we have our Illumina file here. The reads are here. Let's also ls into the assembly. We have everything we need. So we are going to map the Illumina reads, the reads here, to this one here, and then we are going to do some processing and finally do the polishing. So that's how we will do it. We are first going to create a directory called polishing. So I'll say make the polishing. And then we are going to cd into it. So after we are done with the seeding, we are going to create another directory again inside this polishing directory. So I'll say make the assembly. Then we are going to copy the assembly, this file here. We are going to copy it into this directory. So to do that, we will say cp // that means the parent directory. And then we are going to say nanoplot assembly / assembly.fasta. And then we are going to copy it to assembly. So now let's do an ls. We will see this directory here. So in this directory, we are going to find our assembly.fasta file, this file here. So this is it. Now let's proceed. We are now going to index this assembly file here because it's going to serve as our reference sequence. So we'll use BWA. So I'll say BWA and I'll say index and I'll say assembly / assembly.fasta. So I'll run this command. Okay, so indexing has been done. So now we are going to map the short reads. This one here, we are going to map to this one here, this assembly file here. Okay, so don't forget that this assembly.fasta was generated using the long reads. So we are going to polish, and that means we will use the Illumina reads. So let's clear the screen and continue. Let's do an ls again to check our files here. Let's ls into the FASTQ directory again. Okay, so now we are going to map the reads, the short reads to the assembly. So to do that, we will say bwa mem and then I'll say -t, that's number of threads. I'll use 8. And then I'll say assembly / assembly.fasta. This is our reference sequence. And then I'll specify the Illumina reads. So // and I'll say FASTQ / Illumina.FASTQ. And then I'm going to add a pipe symbol. So I'll add this and I'll say some tools view -space-sb. There's a dash here, a space, and then -sb. So take note of that. I'll then add another pipe symbol. That is this one here. And then I'll issue this command also. I'll say some tools sorts, and I'll bring another dash again, space -at, and then I'll say space 8, and I'll say -o, mapping bam. So all that we are doing here is to map the reads and also sort them. And then we are going to generate our BAM file here. We will use this BAM file later on. So let's execute this command. Okay, we have generated a BAM file. So we are going to index this BAM file. So we will use some tools. So we will say some tools index mapping.bam. This will index the BAM file. Let's do an ls to check the file. So we have that here. Perfect. We are now going to use Pilon to polish the assembly. So we will say Pilon -- genome, and that will be assembly/assembly.first_a, and then I will say --fix space or space -- changes, and then I'll add another flag again. I'll say -- unpaired, and I'll say mapping.bam, and I'll say --outputs, and I'll say polished. So the outputs polished means that all the files generated by Pilon will have this as part of their names. This name will be part of their names in addition to the file extensions. So let's execute this command to polish the assembly. Okay, polishing has been done, and we have a summary here telling us the mean coverage. Now let's take a look at the output files. Let's do an ls, and we are going to find some files here. There's a BAM file. There's also the polish.changes file, and there's the polish.first_a. Let's start with the BAM file. So the BAM file here, we can inspect it, and then we can get some statistics from this particular file. So let's just look at the mapping statistics, and then we can discuss further. So let's say some tools flag stats, and let's specify the BAM file. Okay, so we have that here. I want us to look at this line here, the one which has the mapped information. So here we see that 99.94% of the reads, the short reads, map to the assembly. Okay, so ideally we should have majority of the reads mapping to the reference sequence. In this case, the assembly, and that is what we have here. So that means things are looking good. Let's also look at the polish.changes, this one here, this file here. So this has all the changes that Pilon made. So we can look at the contents. Let's do a head and then specify the file. So we are going to find the information. So you will have the changes that were made as well as the context on which these changes were made. So that's what we have here. You can also count the total number of changes that were made. So let's look at that. So you can say wc-l and then specify the polish.changes file. So this will give you the number of changes. So we have 2,891 changes. That's what we have here. And the polish assembly is the polish.first_a file, this file here. So there's the polish assembly. What you should know is that nanopore data can have homopolymer deletions. This can be corrected by polishing with Illumina reads, and that is what we have done. So in other words, polishing can improve assembly by correcting errors that may be present in the sequence data. So now we have our polished assembly, all right. Okay, but it's advisable that after polishing, you compare the draft assembly, the original assembly, to the polished assembly. Okay, so you can do this by evaluating them. So evaluation can be done using tools like Quast. Quast runs some statistics, and then you can compare the statistics for both assemblies. I mean the original one and then the polished one. So you can compare them, and then this will help you to identify the higher quality, the one with the higher quality, and you can use that for the downstream analysis. You can also use the FastA statistics tool, which is available on the Glasses platform for computing the assembly statistics. You can also do that. In this tutorial, we performed a single round of polishing, but it's possible to do multiple rounds. In case you want to perform multiple rounds of polishing, then you will need to write a bash script to do this. You can contact me if you want to learn how to do this. My contact is in the description box. In addition to Pilon, you can also use Recon for polishing long reads. Okay, so Recon uses the long reads themselves for polishing, and I will leave a link in the description that you can use to check this tool out. One activity that you can perform after assembly is genome annotation. We are dealing with a Chloroplast genome, so you can use tools like GISIC. GISIC is an online tool that can be used for annotating Chloroplast genome. So I will leave a link in the description that you can use to access this tool as well. And I'll try to make another tutorial where I show how to use that tool to perform genome annotation. Now, if you're looking for more genome assembly tutorials, then I will encourage you to check out the videos in this playlist.